Swayam Prabha, Digital India, Educated India.
So I'd like to draw the attention of the class towards what we started to discuss in the previous class, and that is the different components of energy of a system. So first thing, what we started talking, what are the components of energy of a system? So we talked about thermodynamic system, this and that, and then essentially we started talking about the different components of energy, and we know that for a system, the components are kinetic energy, the external kinetic energy, so to say, the potential energy, we understand this, and internal energy. And based on internal energy, we had certain reasonably animated discussion on what are the components of internal energy. So the most important component of internal energy is, again, what is known as internal potential energy, or let me write it down. So for a system, we have the internal energy, and the components of internal energy are internal potential energy. It's a bit of repetition I am doing because I have received feedback from few of your friends that they were not very clear about the critical temperature concept. So I will repeat that. Internal potential energy, then we have internal kinetic energy, which is this K into T or KB into T, right? So what we understand from here is that internal kinetic energy is a function of temperature. So as temperature goes up, kinetic energy goes up. In contrast, internal potential energy is essentially the intermolecular interaction, right? So we also discussed in great detail that what can be the types of intermolecular interaction, and these fall into the category of van der Waals forces. So the first or the most important, most sort of abundant or it's omnipresent interaction is the induced dipole interaction, which is also known as the dispersion forces or the London interaction, right? Induced dipole, but I don't care about names, whether you remember names or not. So it's induced dipole interaction. And then you can have permanent dipole induced dipole interaction and permanent dipole interaction. And that way you now understand that hydrogen bond is nothing but an example of a permanent dipole intermolecular interaction. Of course, if you have polarity in your system, the strength of the intermolecular interactions are going to be much higher, right? But even without polarity, there is going to be induced dipole type interaction, and that's all about it. And of course, there is a third set of components which corresponds to the vibration and rotation of the molecules, right? So this we all know, and let's also talk about some of the consequences, immediate consequences. So what are the immediate consequences? Immediate consequences is, so the other thing I'd like to note down, I'm sort of giving a monologue right now, I'll involve the class right away. This interaction, the potential energy of interaction, if you see, is something like A by r to the power 6, and if it is very close, by B divided by r to the power 12. So this is what is called the Lennard-Jones potential or the 612 potential, and it is something like this. So this is the r to the power 6 curve, and this is the r to the power 12 part. So this is a very strong repulsion. When this happens if you bring two molecules in close proximity to each other, and then their orbitals or electronic clouds starts to overlap. So there is a very strong electrostatic repulsion in that particular case, which is captured by this particular part of the graph, which is also known as bond repulsion. I have seen many people writing it as bond repulsion. This has nothing to do with a chemical bond. By definition, van der Waals forces are weak. Yeah, so van der Waals force is, see, there is a misnomer. Van der Waals force, many people consider van der Waals force to be only the induced dipole type interaction. That is one school of thought. But the other school of thought is van der Waals force covers, which in fact van der Waals predicted, all types of interactions, which is a polar interaction as well as apolar interaction. Hydrogen bond is strong, but it is certainly not as strong as a chemical bond, right? So it still remains, right? It still remains an intermolecular interaction. Please do understand that the molecules between the hydrogen atom and oxygen in a water molecule is a chemical bond. However, what you have is hydrogen bond, or a so-called hydroxonium ion, is actually an intermolecular interaction. This does not act within a bond, right? Or it does not act within a molecule. So therefore, if you talk or classify that van der Waals force, this is actually a pedagogy. There is, I and you are essentially talking about the same topic. What are we talking? Is a good point you have raised, and it's a good thing for the whole class to get clarified. The point is, we are now talking that internal kinetic energy of a system comprises of intermolecular interaction, right? That is, I assume that is clear to the whole class. If that is clear, now essentially what we are talking is whether it is van der Waals force or not, that is secondary. You can look into just Wikipedia and check out which force is called what. Something is called the van der Waals force, something is called the London force, something is called the Kizom force, etc., etc. I don't care whether you know the names, because I am not teaching you quantum mechanics. These are important, but more important is to understand. So what is important? If you have two molecules, let's say, how can they interact with each other, or what can be the genesis of the interaction? That is the more important thing. And the genesis of the interaction can be irrespective of whether the molecule is polar or apolar. The first type of interaction that is present is the induced dipole interaction. Of course, the strength of induced dipole is much lower than permanent dipole, and therefore what you are saying, van der Waals force is weak, hydrogen bond is strong. But please do remember, everything is weak compared to a chemical bond. Is that clear? That's why you can, let's say, pour some water from this chamber to that chamber, or take a spoon of water out, right? But you cannot dissociate water that easily into hydrogen and oxygen, because for dissociating water into hydrogen and oxygen, you need to actually supply much higher amount of energy. So this word strong, weak is all very relative. Hydrogen bond is definitely stronger, but stronger to what? Stronger to an induced dipole type interaction. So as I say, both of us are essentially, or all of us, I am sure many of your other friends also have the same concept and ideas. We are essentially talking about same type of, or the same concept essentially, right? We all also know, for example, water has a boiling point, normal boiling point of 100 degrees centigrade. But let's say many of the organic compounds, including alcohol, acetone and stuff like that, have much lower boiling point. You see that if you take some acetone from in the room, the whole room gets filled with their smell. Why? Because they are evaporating. So how is this related to what we are talking? Or in other words, let me frame the question in a very direct form. Most organic solvents have very light, very much lower boiling point as compared to, let's say, a solvent like water. What's the answer? The answer all of you know. What's the answer? If you can use the chat box, the whole class, please. Yeah, so I don't know why the class is so silent today. Only Tanmay and Shraman has given the answer, and that is the answer. So when something evaporates or something boils, interaction is weak. Yeah. And why is interaction weak? Because in organic molecules, there is no polarity. These are mostly apolar molecules. Therefore, the cohesive strength or the cohesive interaction between molecules, right, in the liquid state is only due to induced dipole type interaction. So called van der Waals forces or London forces or dispersion forces or whatever. We do not even go to the names. It's not for us. We understand it's induced dipole type interaction. In comparison to that, as one of your friend corrected, this Vardhan correctly pointed out, that hydrogen bond is much stronger. But that is the difference in the strength. Acetone has a boiling point of 35 degrees centigrade. Water has a boiling point of 100 degrees centigrade. It's certainly not that acetone has a melting point, a boiling point of 30 degrees centigrade, and something with hydrogen bond is as strong as steel, you need to heat up to 2000 degrees centigrade. Is that clear? So everybody understands this, right? Let me just check. Sometimes very simple concepts, I find it's slightly missing. So everybody understands this phenomena of boiling, right? What exactly is happening? Yes. Everybody understands what is happening at the molecular level. Well, Shalini, I have not yet taught you vapor pressure. That's not a good answer. And certainly vapor pressure is not equal to atmospheric pressure. No. That's interesting. So what exactly is boiling? You had a liquid. I am taking 5 minutes to discuss this. I'm not very convinced with the response of the class. And the molecules are going to the vapor phase. That's boiling, right? If it is water molecules, it's gain, I guess, enough kinetic energy to overcome potential energy. Yes, Sridhar, absolutely correct. Absolutely correct. So let me just take a couple of minutes. The response is not very good on the class. I expected a much more overwhelming response. So water at 100 degrees centigrade is boiling to water vapor. What exactly is happening? So things are in liquid state means there is strong intermolecular interaction. Things are at vapor phase means there is no interaction. And what dominates here? What dominates here? What dominates here? Everybody understands that once you have something in the vapor phase, the molecules are undergoing or exhibiting Brownian motion. So their whole system is sort of dominated by kinetic energy. That gives the gas molecules or the vapor molecules the random motion, right? So what dominates as long as it's in the liquid state? Liquid state is Ke. Oh God. No, liquid state is potential energy. Those of you, the messages came in a burst, but let me check. There are few of you who have written Ke. But now I have a doubt whether you were Sneha Bandhu, kinetic energy. Kinetic energy for what? Things are dominated. So since I asked both the things, I will assume that everybody knows the situation, what is going on, and everybody has given a correct answer. So you can distinguish between a vapor phase and the liquid phase as vapor phase is something that is dominated. Late message arrival, not last message arrival, late message arrival. Vapor phase is dominated by kinetic energy and liquid phase is dominated by potential energy. In fact, this will also clarify our doubt, whatever doubt some of our friends had regarding this liquefaction thing. So what exactly are you doing? So in order to boil, what exactly do you do? For boiling, you heat up stuff, right? So if you heat up, what happens? The answer to what happens is very simple, and it is here. The kinetic energy is a function of temperature. Therefore, as you heat up, the kinetic energy starts increasing, right? No, it increase, Adrija. I will request you not to conclude that it immediately increases in the intermolecular separation. It may not increase. What happens is the kinetic energy component of the molecules start increasing. While you see this potential, and this is extremely important. Many people know, but sometimes we do not correlate it. See, the internal potential energy is not a function of temperature. It's not a function of temperature. Therefore, as you heat up, its strength remains the same, right? Its magnitude remains the same. When something is in the liquid form, you need to understand what dominates. Obviously, the potential energy is more than the kinetic energy, because kinetic energy will trigger or will uh, sort of push the molecules to move around here and there. And potential energy is something that is holding them back. Like if it is in a regular class, if I am not there, all of you would like to disperse here and there, right? Because all of you have high kinetic energy. But then I enter the classroom with huge amount of potential energy, grab all of you and make all 140 of you sit together and attend the class. That's the potential energy. So as long as something is in the liquid state, right, the potential energy dominates. So at 100 air, let's say 30 degrees centigrade water, yeah, molecules have some kinetic energy, but it is too low as compared to potential energy. Then you have this hydrogen bond, and hydrogen bond tightly clutches the molecules together, so the molecules cannot undergo Brownian dynamics. Therefore, things are in a liquid state. Now, as you heat up, what happens is that the kinetic energy starts increasing, and as you attain the boiling point, so what exactly is the boiling point? Boiling point is that point that for a given pressure, which is 1 atmosphere, the magnitude, the average kinetic energy of the molecules becomes higher than the potential energy of the molecules. Is it clear to all? Or simultaneously, all molecules now have adequately high kinetic energy. So the potential energy completely fails now, as if the class has ended. Everybody wants to disperse here and there, and the molecules go to the vapor phase. Is it clear? Is this concept clear to all? Now we talk about the difference between, let's say, something like acetone and water. What is the difference? Difference is just surface tension of very little, very little. Surface tension only comes to the surface, not in the bulk phase. I will come to your question. Then comes the question of, let's say, comparing something like acetone or an organic solvent and water, right? So now the clue that I am giving is organic solvents or organic molecules are apolar. And we all know that most of them are apolar. You have some very rare polar organic molecules, but most of the organic molecules are apolar. So now can you correlate why apolar molecules have apolar solvents have lower boiling point, and polar solvents like water has higher boiling point? I guess the whole class will immediately write another flurry of yes sirs. Why? Because since it is apolar, the internal kinetic, internal potential energy is only based on the induced dipole type interaction, the strength of which is lower as compared to something polar like water, right? So potential energy is more because the hydrogen bond is stronger. So when you say strong or weak, so hydrogen, this is a very important learning. You actually learned nothing new, but you got the concept clarified. So hydrogen bond is stronger as compared to induced dipole type interaction. And therefore, most organic solvents have a boiling point in the range of 30 degree to 40 degrees centigrade, maybe 50 degrees centigrade, and something like water boils at 100 degrees centigrade. Is it clear to all of you? I guess it should be clear to all. Yeah. What is the difference between boiling and evaporation? Yes, Sridhar, that's a bookish answer. Doesn't make much sense. No, please don't give an answer, bulk and surface phenomena. Why does some molecules evaporate? Of course, yeah. The two of you have said, and the whole class knows. Yeah, evaporation takes place at any temperature. The whole class knows that boiling, the entire bulk participates in boiling, evaporation only the surface molecules participate. But the question is that if we write this as the kinetic energy, and let's look into at interface. Let's say this is one molecule at the interface. Why evaporation takes place? So Kb into T is the average kinetic energy. It's extremely important to remember its average kinetic energy, and there is always a distribution of the actual kinetic energy landscape. Yeah, it can say partially correct, but it may not always interact with the air outside to gain energy. It might actually pick up the energy from inside also. So yeah, Maxwell distribution, perfectly fine. Surface molecules have less free, very good, Debjyoti. That's also a fact that if you look into the configuration, one of your friends talked about surface tension. I don't want to have a discussion on that now because that's my research area, and then I can keep on talking for hours. So this is, if this is a surface molecule we are talking about, and this is a bulk molecule we are talking about, you can see that the coordination number of the bulk molecules is higher. Like, let's say this figure, this rudimentary figure I have drawn, Here the coordination number is 6. All of you understand coordination number, right? Is the number of molecules that's surrounding the each molecule in the bulk. But here, if you see, going by the figure, here the coordination number is 4, right? So number one is there is less interaction. So or in other words, the surface molecule is under coordinated. This is a very deep concept, but the way we are talking, I think it is understandable to everyone. Is it clear to everyone? Why I mentioned this? If you have a doubt, kindly raise your hand or make a comment. And what's the consequence of this? Under coordination. Chayan, you had a question. Siddharth, partly yes, not fully. I'm not fully, I don't fully agree to it. Because it's not a question of lesser energy or higher energy. Because don't forget, Shayan, where have you disappeared? You had a question on surface tension. So when you were talking about evaporation, all of you made a statement few minutes back. I sort of had to stop people from making. It's a surface phenomena. So there is no point in comparing this molecule with this molecule as far as evaporation is concerned, because this molecule will never participate in evaporation. You agree to it, Siddharth? This molecule is never going to participate in evaporation. So in evaporation, essentially the competitors are only these molecules, all of which are under coordinated. So under coordination is not a necessary condition for evaporation. You have to understand that in a regular evaporation process, you will have large number of molecules on the surface, but let's say one molecule will evaporate, not all will evaporate. Because if every molecule starts to evaporate, you are essentially tending towards boiling. First, all molecules at the surface will start to evaporate, and then all molecules of the whole bulk will start to evaporate. That does not happen. What happens is only one molecule starts to evaporate. And that molecule, actually, as one of your friends have mentioned about the Maxwell distribution, that molecule has higher level of kinetic energy. So that molecule, or the molecule which participates in evaporation, right, has higher Ke. Everybody agrees? I will have an extended answer for this. Compared to what? Yes, Sneh, but repeatedly what you are not understanding is, then if the outside temperature is cold as compared to the liquid temperature, there will be no evaporation. Because then from outside, the atmosphere, it will not pick up any amount of heat. Compared to the other molecules of the surface, Pradipti, great, there's something more. Of course, Pradipti, I'm very happy with your answer, but there is something more to fill up this. Compared to what? Of course, one of your friends has given the answer compared to other molecules of the surface. And its magnitude must be greater than the strength of the potential energy, isn't it? These are the two necessary conditions. There can be some molecules with higher level of energy sitting at the surface, but they may not be able to participate in evaporation. Why? Because though they might be possessing higher level of energy, the strength of the energy, kinetic energy, might still be lower than the strength of the potential energy. Is it clear to all? And when I ask, is it clear to all? You are inclusive. Each one of you must understand. It's not exactly to the bulk molecules, then we're very close to it, but yeah, this is the whole thing. It must be higher compared to other molecules present on the surface, and the strength must be higher than the potential energy that is imparted, right? Then only that molecule can participate in evaporation. Now comes the question what Sneha Bandhu was sort of trying to impress me for a long time now. How does this molecule get this energy? So this molecule which has higher amount of energy, there are several possibilities. This can get energy from the either from the vapor side, right? Or it can also get energy from the liquid itself. Because if you always say it is going to get energy from outside, then you will not be able to explain why, if you keep a warmer liquid on a cold day, there is evaporation. Is it clear to all? Because on a cold day, so let's say you have water at 25 degrees centigrade and in outside temperature is 10 degrees centigrade, typically the temperature that the entire North India, Rajasthan, Delhi sort of sees the whole of winter. Does it mean there will be no evaporation? The answer is no, there will be evaporation, right? In fact, on a humid, sultry Kharagpur monsoon afternoon, there will be less evaporation, because evaporation is also a function of the gradient. It's not only the liquid side property that matters. What also matters is the level of saturation. One of your friends mentioned about vapor pressure. I am deliberately not talking about vapor pressure right now. I will talk about it maybe later today or in the next class. So the excess energy that a particular molecule might possess, which is necessary for evaporation, might come from the liquid bulk also. And you know that, therefore, why these dogs sort of take out their tongue in summer and all these questions to that, answer to that, or why you keep water in the earthen pot, right? Because for evaporation, you take the latent heat or whatever is the heat that is required from the bulk of the system, right? So it's like that. So I guess it is clear to everyone, just confirm that. Okay, now here coming back to the picture of the surface I drew, because a couple of your friends talked about surface, right? So one quick message that we already got from this dirty picture is that surface molecules are under coordinated. So my question is, what is the consequence of this? What is the consequence of this? And the consequence everybody knows. Ayush iron, surface tension, okay? Shivoy, low potential energy, less P. Shomik Sarkar, you cannot ask a question to me. You have to commit yourself. Unbalanced interaction force, okay? Say, what does it mean? Others, what is the consequence? There is a net force acting downward. Downward is a wrong word, inward. अरे inward, inward, वो तो उल्टा भी draw कर सकते हैं ना? It's inward. Surface molecules will try to go in the bulk and to get more coordination number. Well, I do not know how to read the mind of surface molecules and what they want, but the consequence of this is surface tension. Have you ever thought why the word tension? Because since the molecules are under coordinated over here, there is somebody mentioned very nicely, one of your friends mentioned, every surface molecule is in a state of tension. Yes, because of the unbalanced forces. So every surface molecule is in a state of inward pull or tension, right? Yeah, theek hai, Sneh, you don't have to elaborate so much. It's not required. Let us understand. So every surface molecule we draw here has a net inward force, which many of your friends was writing as downward. The reason I did not like the word downward is that you can also have a surface like this, right? So there is a net inward force, and as if what it means is as if the bulk of the material is pulling the surface molecule inward, as one of your friends have written that they want to go inside and increase their coordination number. I don't know whether they want to do that or not, but there is a net inward attraction which is experienced by the surface molecules, and this is what is known as surface tension, right? This is the genesis of surface tension, I would say. Is it clear to all? And then there was a question by Shayon that I have forgotten the question. Can you reframe the question? Or it was something like that. How is rate of evaporation related to surface tension or something like that? Is that the question? Was that the question, Shayon? Some network issues. Nothing is moving here. See, the professors here has actually manipulated the network so that we get 2-3 minutes of resting time by the time all these flurry of these answers come. Yeah, now it has come. Now I have a question. So we talked about the potential of the question Shayan Maiti is placing. Does the potential energy have a role in surface tension? Or does evaporation or the rate of evaporation depend on surface tension? Or does the value of surface tension indicate the nature of the intermolecular interactions? Is the question set of question clear? So I'll just give an example. It's a good discussion. I don't know whether it is related to what I'm teaching you. Doesn't matter to me. So what we understand is that low boiling point versus high boiling point, right? This is related to weaker intermolecular interaction. This is related to stronger intermolecular interaction. This is clear to all of you now? Now my question is there a direct correlation between low boiling point, high boiling point, and surface tension? Is there a correlation? Before you answer to that, surface tension inversely proportional to BP. थोड़ा ज़्यादा ही फंडा दिखा दिया. I'll ask you a question. What is surface tension? And if I ask this question, everybody will give me an answer that it is the energy required to create unit area of a surface. That all of you understand, right? Now, I always give a very practical example to explain surface tension. And that is as follows. And when the students come from the hostels in the morning, it's even easier for me to explain. So every morning in the mess, if you go, all of you hold on to your, it's a bulk phenomenon. All Vivek Surekha, correct, absolutely correct. So this is a block of butter. Yeah, now, okay, okay. So this is a block of butter. And what we do, we take a knife and we cut it into half. So essentially, you are left with two blocks. You can, it's not a block of butter you have to always talk about. You always keep on doing this for many, many things. So when you are cutting with the knife, you supplied some energy? Yes or no? So when you are cutting with a knife, you have supplied some energy, right? What has that energy been consumed for? That energy has been consumed for creating this and its mirror surface, right? We understand this, right? Now we also understand, so this particular material has some surface tension. So what is the total energy required? Total energy required you can calculate very easily. You can calculate or multiply the surface energy divided by the total area that you have created. You get the amount of energy that is required. Now for cutting a block of knife, if you, let's say, bring up a butcher's knife, a big one, jumbo type, or a talwar or something like that, and try to cut it, what will happen? It will cut into two parts, but there will be a loud thud as it hits the bottom surface. So what have you done? You have, by way of using this butcher's knife or whatever, supplied much more energy than that was required to cut this. So this is in a nutshell the example of surface tension. Now, exactly what you are cutting, I mean, what is this cutting action? So let's say this is where the line along which you are cutting the block. So exactly what are you doing by means of this cutting? Can the class tell me? Is the question clear? Exactly what are you doing to create the new surface. And as I keep on telling, everything must be crystal clear. I mean, you should understand things pictorially, like a cartoon. Cartoons have the biggest impression on our mind. We have studied them in our childhood and we still remember. And what you have, applying pressure is one part of it, but what exactly are you doing? Breaking intermolecular forces. Others, please. Tanvi, that is exactly what I was apprehending. And now Vivek and others have joined. Provide energy to increase surface area. That's a philosophical answer, Vashvin. Others, please. What exactly are you doing here? No, you are not increasing the potential energy. No. What exactly breaking the interaction? Very good. Devjyoti, very good. Separating these molecules. How? Sridhar, you have already given an answer. Others, please. I am not teaching to 7 people in the class. For that I wouldn't have been shouting at the top of my voice. Creating a gap. But what are you doing? How are you separating them? What exactly? You are actually overcoming something. Here was a molecule, here was a molecule. You are turning something off. Turning off the intermolecular interaction between them. Breaking surface tension. No, Shubham Kumar. Please stick to point. Breaking the interaction. So you are essentially turning off or overcoming the interaction between the molecules. And my worst fears have turned out to be true. By some of your friends mentioned that you are breaking bonds. The reason I ask this question is many people make this mistake when they say that you are breaking bonds. You are not breaking bonds. Not breaking bonds. You are simply cutting. Are you creating some new material? The answer is no. It was butter this side, it is butter that side. You are not creating butter dioxide. So you are not breaking bonds, because if you make or break chemical bonds, there is a chemical reaction. So all you are doing is you are simply overcoming the intermolecular interaction between the molecules which lie on both sides along which you are going to cut. So all you are doing is you are turning off all these interactions, and the collective total interaction along the whole interface gives you the amount of energy that is required to cut the molecules, cut this block. Is it clear to everyone? And therefore we understand now your effort to cut a material which is apolar will be lower as compared to your effort of cutting a material that is polar. Is it also clear to everyone? Because if you have polar interaction, then the strength of the intermolecular forces is going to be higher. Is it clear to all? And if we understand now surface tension from this standpoint, we also understand that, I'll probably use a fresh slide here itself, not in the previous one. Evaporation will be lower in liquids with high surface tension. And we also correlate higher surface tension is used by gamma. Higher gamma liquids are likely to show higher BP. One of you mentioned very nice, very well thought out answer. That was very nice answer. I sort of really liked it. That so these all can correlate now. One of your friends, I cannot really go up and down and figure out who that was, but I really like that, sir, surface tension should not matter the boiling point, because boiling point is a bulk phenomena, and surface tension is related to the surface. Agreed. Surface tension, however, what you need to understand at this point of time is surface tension is nothing but a manifestation of intermolecular interactions. And intermolecular interactions are present everywhere, at the surface as well as at the bar, right? Cutting butter and removing a spoon of from, it's no difference, absolutely no difference. Liquid does not have a surface because liquid does not have shape. All you are doing is, there was a glass of water, you have taken a spoon. So you are supplying some energy to overcome the hydrogen bonds of the, let's say, 340 molecules of water that you have picked up in the spoon. There is absolutely no difference. In both the cases, don't forget, Rishi, that you have to supply external energy. Is that clear? And when I get questions like this, I do understand the class is following in a way I want. Not exactly the classical pedagogy, but understand science in our own mental horizon with the example of very, very simple but practical examples. When this type of question, cutting of butter, picking up a spoon of water, these all the time we do. But we do not have, see, you actually are using your right hand and a spoon. Spoon gives the shape, nothing else. But your right hand, you are all the time spending some of your metabolic energy, right, in doing all this. And why on earth you have to spend the metabolic energy? Because there is surface tension. You actually are supplying some energy to overcome the cohesive interaction of those many molecules. You are turning that interaction off. Is it clear? Is this concept clear to the whole class now? Is this concept clear to the whole class? So I will actually go back to this particular part of the slide, which was very nicely written. So we can actually correlate. It's a very interesting correlation. Glad I talked about it. I don't talk about it every year. Low boiling point liquid, high boiling point liquid. So what we, now the class is knowledgeable. So we all know that it's weaker strength of intermolecular interaction, stronger strength. So it is likely, no rule of thumb, likely it is apolar, likely it is polar. This will have higher evaporation, higher rate of evaporation. This will have lower rate of evaporation. And this is likely to have lower boiling point. Oh, yeah, so lower boiling, higher boiling. So is this now whole picture clear to all? So yeah, there's something I missed out. See, I don't teach from any notes. I'm not teaching today from any notes or whatever. Therefore, I'm getting a little lost. Yeah, lower surface tension. Higher surface. Is this correlation clear to the whole class? If you understand, my 1 hour worth is absolutely okay. Please mute yourself. One of you, it's getting unmuted again and again. Please mute yourself. So this part is clear to everyone. Now let me ask a couple more questions. Thank you very much. Have a nice weekend.